is doing like well, hands-on as best we can investigations of the gas laws. You'll basically see. Alice, is that you? Alice? Oh. So we'll basically see how tweaking one particular part of the conditions that a gas is under affects the conditions of all the other parts, and should be able to plot the relationships between pressure, volume, temperature, and number of moles. And so there's a new law here that we didn't really talk about in class, but it's pretty straightforward. It's the Gay-Lussac law. You can tell it's another famous chemist with a French last name, as most of them are. And so the relationship there is between, be able to draw on this thing. The relationship there is between pressure and temperature. So Boyle's law shows us the relationship between pressure and volume. And Charles' law shows us the relationship between temperature and volume. Now we should be able to realize that pressure and volume are pretty much the two sides of the same coin. That if we squeeze a gas from a larger volume into a smaller volume, we know that the pressure is going to go up because pressure is a result of the gas molecules hitting the sides of the container. So if we make the container smaller, there's going to be more collisions with the sides of the container, and the pressure is going to go up. So Gay-Lussac's law basically says the same thing's going to happen if we increase the temperature as well. That if you increase the temperature, those molecules are going to move faster, and the faster they move, the more chances they have to hit the sides of the container. And so it's going to affect the pressure as well. And then finally, Avogadro's law basically just says, the more gas you have, the greater the volume. And that is sort of, that's one of the most basic laws here, and explains that, if we do a reaction that releases gas, the more gas that is released, obviously, the more molecules of gas have been produced, the more moles of gas have been produced. And so we'll be able to manipulate all of these different things and be able to show the relationship between them with a graph. So kind of what I'd like to go through is, for each one of these laws, we're going to devise a slightly different experiment and collect some data, changing one parameter and seeing how it affects another parameter. And so you should be able to make a table, a data table with one parameter on one side, changing parameter on the other side. I want you to be able to identify which one is the dependent variable and which one is the independent variable. Can people tell me in an experiment which is an independent variable and which is dependent? That's going way back to the beginning of class. Which one is an independent variable?
The independent variable is the factor that you can control.
Right. It's the one that you move, that you change. Exactly. It's so if you are changing the temperature in an experiment, and let's say the rate of the reaction increases because you changed the temperature would be the independent variable, and the rate of reaction would be the dependent variable, because it depends on whatever the condition was that you changed yourself. So what we're going to do today is change our dependent variable, and the dependent variable should always be, let me draw this again, dependent variable should always be on the x-axis. So x is what we change, And then Y is basically the effect. So if we change X, if we increase X and Y also goes up, we can see that there's a direct relationship between X and Y. And some of these we're gonna see that it's not linear. And hopefully you should be able to explain why that is, okay? So let's have a look at our first reaction we're gonna do. So first I want you to hopefully been able to find the simulation online. If not, there's either you can click on it if you have it open, or if you don't have it open, you can just, I don't know, type it in here. It might be a little bit tricky. But it's basically just a virtual gas law page, which we can change all the different parameters. We can change the temperature, we can change the volume, we can change the amount of gas, and we can see instantly what the effects are of the different changes. So if we look around here, we've got our chamber with the gas in it, and we can even like count the individual molecules. So the numbers of the molecules in there is related to how many times we pump here. So this is the pump. Each time we sort of press it, it will go down and release a set amount of gas. And we can choose whether or not we want a small molecule of gas, gas A, or a large molecule of gas, gas B. And you can play around with, all A or all B, or you can make mixtures of each and see how it affects your results. Here's a pressure gauge, which will show you the pressure in atmospheres, so you don't have to convert them to torr or millimeters of mercury or kilopascals or whatever, any other form of pressure. It's straightforward atmospheres. Here is like a piston where we can change the volume of the container. So the largest volume possible is 1,000 liters. And if we press on this button here, we can reduce the volume and watch the changes that take place because of it. And if it's smaller, we can increase the volume as well. So over here, we can change the temperature inside. So if we press on heat, the temperature will just continue going up and up and up until we hit it again and it stops. And then for cooling, the same thing. Just press on cool and the temperature will go down and down and down until we hit cool again and it'll stop. All right. And then it just gives us the temperature directly in Kelvin, which is nice. So we don't have to make conversions from the Celsius or whatever else. And then finally, if we want to start another experiment and release all of the gas, we have this gauge here. This valve will release the gas. So we just press on this right here, and it will open, and the gas basically will come venting out this little tube right there. And so it'll empty, the volume will go to zero, and then we can start again with a different amount of gas, or switch gas A and gas B, or a mixture of whatever we want. Now you may have noticed over here on the side, it gives you, we talked this morning in class about the average kinetic energy or the average speed of molecules at different temperatures. And here it gives you a measure of the average kinetic energy of the molecules inside the container. And here RMS stands for the root mean speed, which is basically what's the average speed of the molecules in there in meters per second. So we can see in this particular example at 165 degrees with 1,000 liters of volume, and 2.8 atmospheres of pressure. The average speed of the molecules in there are 359 meters per second. And you can see as you change all of the different parameters, how the speed changes. And so you may be able to see the relationship between the speed and the pressure, or the speed and the temperature, and how they all relate to each other. So let's go to the first example. So what I'd sort of like you to do is write, just the usual sort of report, title, purpose, and procedure. And then you don't have to write down exactly what's here. Basically, just summarize what you're doing. And then here's what your data chart will look like. Basically, just fill in the different volumes. Like say, look, at 100 liters, my pressure was, 1 atmosphere, and at 235 liters, it was, 2.38 atmospheres or whatever. And then, as many, I think I recommend like at least 5 different volumes here. And then you're going to plot these at the end. Which variable was independent, which variable was dependent, and then graph pressure versus volume, okay? And then we're just going to do each of the different gas laws separately. So in your results, you'll have the data table, you'll have a plot, and you can answer these questions inside the results section. And at the very end, there is some post-lab questions for the very end, okay? So let's just go back to the very first experiment and see what we're going to do. So first we're going to remove all the gas from the containers, because I think when you open up the page, I think it has some gas already in there. So what we're going to do is we'll just empty that, so we'll all start at the same place, and then just add 2 pumps of gas A into the container, and then see how many gas particles are in there, and just describe what their motion is. Is it random? Are they all moving in the same direction? Are they moving in different directions? What happens when they bump into each other? So then we're going to check the temperature of the container. I'm not sure exactly what it starts out being. And then we're going to adjust the volume of the container. We're just clicking on the down button, the one that was right next, just to the right of the container. And as you click on it, it will decrease. And then we'll just take 5 or 6 different volumes and see what the pressures are. And then we'll just go to the next, law, and we'll change something else and see what the result is. But let's go to, if you don't have the page open, and now would be a good time to sort of open it up. So I've got it open here. You can see, yeah, it's already got some, I don't know if you got the same thing when you just opened it, or whether I was playing with it last night. Either way, let's just go ahead and hit the pressure valve, and that releases all of the gas. Okay. So is everyone? Yeah.
Are you on the actual simulator?
Yes. Can you not see it?
No.
Yeah, we don't see it.
Okay. Oh yeah, I think I need to share it again. Here we go. Can you see it this time?
Yeah.
All right. So yeah. So what I did was I just clicked on. I just clicked on the lever below the pressure indicator, and it releases all of the gas. And what temperature do people have right now? If you just open it, actually, why don't I just do that? Why don't I just refresh it?
325 should be the
25, right. Okay. All right, so so that releases all the gas.
Is there a easy way to control the temperature? Because it goes down really quick and goes up really quick before you could hit the off button, so it'll be pretty random. Like I can't get it to like 325 if I wanted to. It starts at 325, but
couldn't get it
if I
to
switched it,
65.
Yeah, well, the thing is, for this particular experiment, it doesn't matter what the temperature is, as long as it stays the same throughout. And that's one of the questions in the handout, is that which things need to be made constant for these to work. So you need to identify which things are changing and which things need to remain constant. So, in particular, for looking at Charles' law, for looking at the relationship between pressure and volume, the temperature can be whatever, but it needs to be the same throughout. I mean, my temperature could be, 10 degrees. That's fine, as long as it stays that temperature all the way through. Okay.
gotcha.
So I'm just gonna set mine at, mine's at 370. Yours can be whatever temperature you want. So I'm now going to put in 2 pumps of gas A. So you just select gas. That selects gas A. Make sure these are small. I'll put 2 pumps in there. So that would be my first data point. So volume is 1,000 liters, and my pressure would be 1.82 atmospheres. So I write that down as my first data point. And I make a note, I also should say somewhere, maybe in the title of both on the plot and on my data table, what the temperature is. So I'll put down, volume versus pressure at 370 K or something like that. And you can see all the little molecules moving around. And it gives you an idea of how fast they're moving over here. The RMS, you can see they're moving pretty quick, 1,754 meters per second. So that's really, really fast. And as they hit the sides of the container, you see the result in the pressure of 1.82 atmospheres. So now I want to reduce the volume. So I just click on the lower one, and I can stop it wherever. It doesn't matter. You can stop it at whatever it stops at for you. You can put it down to like a really low volume. But basically what I'm looking for is like, 5 or 6 points between the beginning, which was 1,000. So I'm just going to click on it. Okay, so it's 790 liters. Now notice the speed of the molecules has not changed, right? So let me just note that here. The molecules are exactly the same speed they were before, but the pressure's gone up. So why would that be? The
Less
molecules,
volume?
so so there's less volume, but what does that mean for the
They're all bouncing off
pressure
against
higher?
everything.
But why is the pressure higher now? I mean, they're not moving any faster than they were. So what actually happened to make the pressure go up? I mean, yes, the volume was decreased, but what happened?
They're moving
They're
faster.
They're what?
Moving faster.
They're
Vibrating
not.
faster.
No, they're not.
They're just forced to interact closer together. So
Forced to interact with each other?
I remember that was, I don't remember if it's with each other or with,
So if two
I
gas
remember you mentioned
molecules,
this once.
right, if two gas molecules collide with each other, does that have any effect on the pressure? There's only one thing that has an effect on the pressure. What is that? One thing results in a higher gas pressure inside the cylinder. What is that one thing?
Temperature?
Excuse me?
Temperature? Is it
No.
temperature?
No, the temperature will change the pressure, but it's the temperature or the lowering of volume changes something that happens inside that cylinder that results in more pressure. What is that thing? What is the physical thing that happens that results in gas pressure?
I mean, there's still the same amount of particles, just in a smaller volume.
Right. What does that result in?
Pressure?
Mm-hmm. Why is the question? Why does that result in a higher pressure?
I don't know. My brain isn't making that click.
Is it because that since the volume is lowered, the pressure will rise up because the space that the particles used to have are more compressed now.
Mm-hmm.
Like the area that they are moving is more compressed, and the
But
pressure.
what does that result in, though? What happens to the particles when they're in a smaller volume? Something happens to them it's different. So the speed of the particles moving hasn't changed, but something has changed slightly. So we went from, so our pressure has gone.
They're still moving the same speed, but you
Mhm.
just decrease their volume, so they're hitting the wall not faster, but in a smaller area, causing pressure.
You're hitting each other instead of
They're hitting the walls more frequently.
Frequently, okay, that's the word.
That's what's happening. Yes, they're hitting the walls more frequently. And so because basically the volume has gone down, there's less place for the moving gas molecule to go before it hits the sides of the container. So it's more likely you've reduced the distance that a molecule needs before it makes contact with the sides of the container. And so as you reduce the volume, the gas molecules have less room before they hit the sides of the walls. And so they make contact with the walls more frequently. And the more frequently they make contact with the walls, the higher the pressure. Because it's the actual contact of the gas molecule hitting the side of the container that results in pressure. And the more that happens, the higher the pressure. So when you increase the temperature, they're moving faster. And so the faster they move, basically there's now sort of less space. There's less space before they come in contact with the side of the wall as well. And so the pressure goes up. And you can see this as we go even higher. So you can see how they're hitting the sides of the wall now. But if I go down, now they're almost constantly hitting the sides of something. They're either hitting the piston, the bottom, or the sides of the container. Because they really can't go very far at all without making contact with one of the sides. And you can see the pressure's gone way up. And I think the smallest volume I can go down to is 150. And now you see they're just basically constantly making contact with the sides of the container. So what I'd like you to do is to take 5 or 6 different volumes, write down the pressures, and then you can also make a note of the temperature, and you can make a note of the speed as well. Just to show that the speed is, noticed, it has not changed. I increase the volume, I decrease the volume, the speed, and the amount of energy the molecules have is exactly the same. So nothing has changed there.
Will it not change like at all?
No. The energy of the molecules is exact, because it's the speed they're moving. Notice as I drop the size, they don't go any faster. They just hit walls more often than they did. They're moving at exactly the same speed.
Is it also like because of the temperature too? Like because there's like no change in temperature, so like there's no-
Exactly. Yes, because the kinetic energy is directly dependent on the temperature. So if we add more heat energy, let's just increase the heat energy. If we increase the temperature, note that the kinetic energy and the speed has gone up. So now that I've increased it to 600 degrees, you can see that the speed of them has gone from like 1700 up to 2200. So they're moving faster. And now that they're moving faster, they have more chance to hit the sides of the container than they did before. They will hit it more times per second than they did before because they're moving faster. And so the pressure goes up also. So let's go to the next experiment. So everyone sees how that one worked?
Yeah.
So let's go to the next. Can you see the Word file? Do you get the words? On,
No,
No.
You gotta switch
I
over.
need to go back and forth. Okay.
Yeah. So, sorry, just asking. You just
That's a
want
drag.
us to take a note of the temperature, pressure, and the volume and the speed. Just write that down.
So for Charles' law, you're changing the volume. So your plot should have your data table should have volume as pressure, right?
Right.
But you should somewhere you should have somewhere in the data table, like on the title or something, you should say what the temperature was. Make a note of what the temperature was.
Okay.
That was Charles. So then we plot the, wait a minute, no, that was Boyle's law, sorry. So we want to connect the line. We want to plot pressure versus volume. You'll determine which one was the independent variable and which one was the dependent variable. Remember that the independent variable goes on the x-axis. So whatever you change should go on the x-axis, and then whatever was changed should go on the y. And then have a look and see what shape that plot is, okay? So now we're going to go to Charles' law. So which one of, now we're going to be changing the temperatures, okay? So we'll empty the container again, and we'll put 2 pumps of A. Also wanted to mention, I wanted people to repeat the same experiment using gas B or a mixture of A and B and see, do you get the same results or not? You may notice that the kinetic energy and the speed will be different, but will your results be different? Okay, so now that we're doing Charles' law, we're basically going to be plotting changes in temperature versus volume, okay? So we're going to empty the container and again put some gas A into it. We'll reduce the volume to 500 liters, make a note of the temperature and the pressure, and then we'll just start decreasing the temperature. what happens to the volume and the pressure, okay?
Are you on the? Oh, are you still on the dock? Or are you on the
Yeah,
simulation?
can you, you're not seeing the doc?
Oh no,
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 yeah,
no, no.
we
I
can
just
see
wanted to
the
make
doc.
sure. I just wanted to
Okay.
make sure.
Okay. Yeah, so let's go back to new. Yeah, this stinks. Oh, I should just screen. If I just share the screen, maybe that will. Okay, here we go. So everyone can see everyone can see the screen again.
Yeah.
Yep.
All right.
You're good.
All right. So I'm going to empty everything. Cool this down to some temperature. So I'm going to put a couple pumps of A in here. And I'm going to go up to 500. Oh, try and get it to around 5. Here we go. Now, so we're going to try and increase the temperature, decrease the temperature, and see what happens to the volume. I think we can get the volume to change rather than the pressure. We will see. So if I increase the temperature, let's see what happens. Yeah. So when I increase the temperature, notice that the volume increased, right? Did you see that?
Yes.
So I write down my initial temperature, the initial volume, and the initial pressure. Okay?
Wait. So we're supposed to record temperature, volume, pressure, and what was the other one?
So last,
Speed, right?
well, you can make a note of the speed, but really it's the volume we're looking at this time. So last time we looked at the relationship between the volume and the pressure. This time we're looking at the relationship between the temperature and the volume.
Mm-hmm.
Okay, so let's just start over. So
No, I was just wondering because like I'm just making my table right now, and I was wondering like should I record temperature, volume, and pressure, or should I just stick with whatever's on the dock?
stick with whatever's on the dock, but yeah, I would certainly make a of the speed and see if
Got
there's a
it.
relationship between the speed and the either the pressure or the volume. So here I've got to start with a temperature, and it can be whatever. Let's see if I go back. So I think 325 is the
The default when you refresh
default,
the page.
right?
Yeah.
All right, so I'm going to empty it. And then I'm going to put 2 squirts of A in there. Then I'm going to reduce this to 500. It may take a little, it's a little tricky to do.
Wish you could just.
Whatever volume, it doesn't really matter. Just change it to like around half. Because man, I get it. There we go, got it. So then I write in my notes. So at 325 K, 500 liters, 3.2 atmospheres of pressure. Okay. Then I heat it up a little bit. Oh, you could also make a note of the speed, 1,644 meters per second. Now I'm going to increase the temperature a little bit. So I went from 325 to 400. Notice what happened to the volume. The volume went from 500 liters to 615. Even though it's exactly the same number of gas molecules as before. So what's different? What happened when I increased the temperature? So they started moving faster. What else seemed to change?
Alice says pressure.
No, it didn't.
The volume.
0.2 atmospheres. Yes, the volume increased, but what happened?
Their kinetic energy
Molecules.
increases too. Their kinetic energy increased too.
Right, their kinetic energy increased, but they're not, see, they're hitting the sides of the container just as often as they were before. That's why the pressure is not increased. They're hitting the sides of the container the same rate, exactly the same rate they were before. So the pressure is not increased. What has increased though? Something else has increased. Maybe a little bit more obvious as I increase the temperature some more. See if you can see what it is. All right, now I'm up to 570
Speed.
degrees, 575 K.
And speed
It's
and kinetic
increased.
energy.
But what else is? But what do you notice about the molecules?
They're moving around.
They're moving
Fast-
around faster.
faster.
But what else about them?
They're colliding more.
Mm-hmm.
Just more space in between from
There
where
you
they're hitting.
go. Yes, there's more space. They're separated more. There's more space in between them. And because there's more space in between them, the volume increases. So the pressure stays the same because even though they're moving faster, the size of the container is exactly the same way they did before. But since now that they're moving faster, there's more space in between them. And the greater space in between them influences the volume. And so the volume goes up as we increase the temperature. So this would be like, taking a balloon and putting it in the freezer and then taking it out and putting it in the back of a hot car. So the pressure is the same, whether it's, it's atmospheric pressure, whether it's in your fridge or whether it's in your hot car, but the temperature's different. So now when the molecules start moving faster, the volume increases because there's more space in between the molecules as they move faster. So what I'd like you to do is to take about 6 different temperatures. It will max out once you get to, I think 600 looks to be as high as you can go. And you can cool it all the way down to I think 10. It's the lowest. So at 10K, now the pressure actually goes down because the volume is this low. The volume can't go to 150, it looks like. So basically what we're looking for is, can you get 5 or 6 different volumes at the same pressure to show the relationship between heat, the temperature, and the volume, okay? All right, so let's empty this out and we'll go to the next one. So I'm gonna go back to let's see if I go right to the doc. Can you see the doc now?
Yeah.
Oh, so I just need to share the screen rather than, that'll help. Right, so that's Charles' law, looking at the difference between temperature and volume. Now remember, when you're doing that, you want to be careful because I showed you that there are points in that in that simulation where the pressure will go down, and because the smallest volume, I think it stops at like 150 liters. So you want to have 4 volumes in between about 150 liters and 1,000, because between there the pressure won't change. If the temperature goes too low, the pressure will go down too, and you want the pressure to be constant. Because when you're varying one thing, when you're varying changing one variable and looking at the effect on another variable, everything else needs to be constant to see the direct relationship between those two. And so for temperature and volume, the pressure has to be constant. So be very careful. You make sure that you look and see. So whatever temperatures you choose, make sure the pressure stays the same, okay? So Gay-Lussac's law. Here, now we're going to look for a relationship between pressure and temperature. So this time, we're basically going to fix the volume and change the temperature and see what effect it is on the pressure, okay? I think there should be a little lock on the...
There is to lock the volume.
Oops, mouse. Yeah, so there should be a lock here. So what we'll do is let's do gas B just for giggles this time. All right, so I'm going to put 1, 2, and then they go down to certain volume, then lock it. So now it'll stay at 500 liters, okay? So now I look, I see, so at 295 Kelvin, 500 liters, this many moles, 2 moles basically of gas B. This is my pressure, all right? Now I'm going to heat it up. The 430 K, I've gone up. Notice that the speed has increased and the pressure has increased. So why is that? As the speed has increased, the pressure's gone up too. Why would that be? What's different about the molecules now that the temperature's gone up?
They're vibrating faster.
Excuse me?
They are vibrating faster.
Not just vibrating faster. That's not really what it's not. This isn't vibrational energy we're talking about. This is kinetic energy. And what does kinetic mean? The word kinetic has a very specific meaning. You know what it is?
Motion?
Motion, exactly. So it means they're moving. So yes, I mean they may be vibrating slightly more frequently, but really it's the vibrations of a molecule are dependent on the bond energy. It really doesn't have much to do with the temperature. I mean, it's a little to do with the temperature, but not as much as the kinetic energy, where the molecules themselves are moving faster. So now that the temperature's gone up, they're moving faster. Why does the pressure go up? What's happened now that they're moving faster? What's happening more frequently than used to happen? Now that they're moving faster. Something happens now that they're moving faster that results in an increase in pressure. What is that?
particles are bigger?
They didn't get any bigger. They're the same size as we started. I just put the big ones in this time, but they're the particles themselves are the same size they were before. The temperature hasn't made them any bigger. They are moving faster, and so that results in something happening that increases the pressure.
Someone said that they hit the walls more frequently, which builds up pressure.
Exactly. That's right. Move. The faster they move, the more likely they are. Oh, man. Someone is making this horrific sound. Thank you. Yeah, the faster they move, the more frequently they will contact the side of the container. Just like, the faster you drive your car, the more likely you are to hit a wall or a tree. So the same thing's happening here. So as we increase these, so that's a 430. Let's increase the heat a little bit more. So at 540, you can see the RMS or the root mean speed has gone up again. They're moving even faster, and they're hitting the sides of the container more frequently, and the pressure has now gone up again. So what I'd like you to do is to take 6 different temperatures, both cooler and hotter. Let's see if we get down to very cold, watch what happens. So at 10 Kelvin, you can see they're barely moving at all. And when they're barely moving at all, they very rarely make contact with the side of the container. And because they're barely making contact with the sides of the container at all, the pressure drops to almost 0. So we can see like 0.10, 0.1 of an atmosphere. Whereas before we were getting like almost 7 or 8 atmospheres of pressure. Exactly the same amount of gas, but since the particles are barely moving, the pressure is extremely low. And then if oh, go ahead.
Oh, I was just gonna say I tried going to where your temperature and pressures are at, but I got 0.05 instead of 0.10. Does that
okay.
matter? Or is that just like normal?
I don't know why. I should have got the same. Oh, did you use a different gas? Did you use A instead of B?
No, I'm using B. I mean, it might be because it's very hard to get to like exactly 500 with this whole button pressing thing. You can't make it.
Yeah,
exactly.
it could be. Yeah, just make a note. So again, on your data table, you should have the relationship between temperature and pressure at whatever the volume is.
Mm-hmm. Okay.
Okay. Yeah, so you can see like at 600K, the pressure is basically now 60 times higher than it was at 10. So you should see that, if the temperature is 60 times higher and the pressure is 60 times higher, is that a direct relationship or an indirect relationship? Okay. And then the last one, I'm basically leaving it up to you to figure out how to do that experiment. So what I'm going to do is, so that is Avogadro's law. So what I'm going to do is get down to a regular temperature. Or actually, this is what you get at the beginning. So I'm going to remove the gas completely. So what I want you to do is basically play around with the different conditions, the temperature, what temperatures you need, what pressures you're going to need. And so each time we put in, oh, wait a minute, where's our gas A? It's not, oh, there, whoops. Each time we put in some gas A, each pump, basically we're going to refer to that as like a mole, okay? And what I want you to do is to figure out conditions where you see the relationship between the number of pumps you put in, number of moles you put in, and the volume. That's Avogadro's law. Now you can see here, just one pump gives me 1 atmosphere and 800 liters. If I put in another one, the volume goes to the max. So I'm going to have to change something in order to see a linear relationship between the number of pumps or the number of moles of gas and the volume. That's Avogadro's law. So you're going to have to figure out a way to show 1, 2, 3, 4, 5 pumps of gas in an increasing volume without getting to the maximum volume. So I'm going to leave you guys to try and do that on your own. So any questions before sort of like, you know, what I'm expecting on the report or anything like that?
Can you give us like a quick summary of it, like you know, like step by step, like a short summary of this lab report?
Sure. Let me go back to the right. So we should start with, you know, title, name, sort of, you know, purpose, and then sort of a procedure. You can even include a you know, a picture like this if you want to. Just briefly what the procedures were for looking at each one of these different laws. And then for Boyle's law, show me what the, if there's any questions in here, answer them. Which one of the 3 variables cannot be changed? So you answer those questions in there. And inside the results, have a chart. What was changing, what was being changed, and what things are being held constant should be in the chart. And then below the chart, there should be a plot of the data that's in the chart, okay? Answer these questions, and you can just break, you know, you can have them separated, but the first one would be Boyle's law, and then show the results for Charles' law, answering the questions for Gay-Lussac's law, and then finally for Avogadro's law. So you're going to have to tell me, and for the Avogadro's law, you're going to have to tell me what the procedure was, because I don't know what everyone's procedure is going to be slightly different, hopefully. So you're going to have to tell me what you changed, and then give me a plot of moles or, you know, pumps of gas and volume. And if it says to compare gas A and gas B, do that. So because I think for Charles' law, it says repeat the analysis with gas B and comment on any difference in the results, okay? Same with Boyle's law. They get asked for repeat the same experiment with gas B, do you get the same results? And did you, didn't you, and explain why the results are the same or the results are different. And then that's, then answer the post-lab questions, and then that's it.
Oh, okay. Thank you.
Okay? Any other questions? Remember, it's, yeah, send me a note. I usually generally respond to emails or Canvas messages fairly quickly. So if you have any questions on how to do these, don't sweat it. If you're panicking, it's like, oh my God, I'm never going to get all this done. You know, you want to take an extra week, that's fine. Don't worry about it. We will have to have everything passed in before the end of the term. And that's coming up about a month or so.
So close.
Yeah, I know. It's unbelievable, isn't it?
But yet so far.
So close yet so far, yeah.
All right. So, if there are any other questions, I will leave you to play with that, and I'll put an announcement in about the tests next Thursday, and I'll try and remember to include these as to make these as assignments in Canvas. So I've been forgetting to do that. All right. Have fun.
Professor.
And thank you.
Oh, yes. Oh, question. Yes.
It's from the last lab.
Okay.
So when I was doing the solid sodium hydroxide, you know,
Mhm.
where there's a tear button from the scale.
Mm-hmm.
So when I would try to like put 1.0 grams, the scale gives me 0.5. Is that normal or is there something wrong with my measurement thing?
Yeah, I would just, I think with that simulation, yeah, you can just, like, I think you just click on the sodium hydroxide and say, give me, 0.50 grams or give me 0.10 grams. You can just do that.
Just when I like type put 1.0 grams and then the scale reads 0.0. I mean, the scale reads 0.5. So I
Weird.
was kind of confused because I was not sure
You wonder which is which, right? Yeah.
if I'm supposed to use 1.0 grams or 0.5.
I would just take the container, the NaOH container, and put it over, I think whatever you want to weigh it, whatever you want to put it into, and just say, so dispense, just say accurate or precise, and then just type 1.00 grams, and it will put exactly that much. Don't worry about weighing it.
Okay.
Yeah.
That's it. Thank you.
Okay. All right. Anybody else before we go? All right. Stay well, everybody. Try and have a good weekend.
Bye.
Okay.
Thank you.
I know it's not going to be very much fun, but
Professor, are you
Oh,
gonna
yes.
have like office hour?
Yes. Yeah. Yeah. Actually, I'm gonna have one tomorrow at 10.
Oh,
Yeah.
okay. Okay. Because I
What?
have like some question from like the last week recitation. So
Okay.
You're having
Yeah.
a what?
I'll just make one for tomorrow at 10 in the morning.
okay, thank you.
All right. I think a couple different people wanted to meet.
Oh, okay. All right.
All right.
Bye, Professor.
All right. We'll see you later. Bye-bye.